My name is Eric, and I'm the team lead for this group. This is Toby, Kevin, and Jeff, and we're here to show you our cognitive radio multimedia network testbed for multimedia communication, or COMET for short. I'll be describing you the background information and a quick overview before Jeff will delve into the high-level design, followed by me outlining the technical description. Toby will demonstrate our testing methods and their results. Kevin will talk about our planning and methodology and summarize what we learned from this project. Finally, I will walk through a quick demonstration of our application and open the floor for any questions. So this project explores the field of wireless communications, and we all take this field for granted. The fact that we can communicate globally, whether through our home routers, our cellular carriers, that we can browse social media or message one another. Even when we make a simple phone call or tune into our radios in our car. The fact that almost everywhere we go, there is information being spread all around us in the form of radio waves at different frequencies, whether it be the range of 100 megahertz on our car's radios, or even 2.4 gigahertz from our phones and laptops. The devices we use are purposefully engineered to help interpret the electromagnetic radiation at specified frequencies. For our project, we utilize something known as software-defined radio. Now, traditionally, the devices we use to send and receive wireless communications are often designed to accomplish one task, or listen to a single or small range of frequencies. SDR is a platform that allows an individual to define their own radio components in software, rather than having to design individual circuits to create their product. For example, the picture right here is showing a simple design of an FM receiver. Something that would be in a car, tuning into the radio. With SDR, we can have a base hardware component, often a field programmable gate array, that can be interfaced with to define each of these radio components with software. And it's designed to create a working FM radio with the code you develop on the platform. In our case, we are using a high-level SDR made by National Instruments called the Universal Software Radio Protocol, the USRP, to send and receive text and images between one another in a confined testing environment. The USRP is interfaced with a hardware driver called the UHD to program the FPGA through an Ethernet connection, using in our case an open source program called GNU Radio. This software allows us to graphically place and connect various radio modules together, kind of like the FM receiver I showed you earlier. And this generates low-level code that's interpreted on the USRP to easily deploy our application. Now I'll let Jeff take care from here on.
So our customer gave us certain requirements that he wanted to see were met for this project. First off was to design a network testbed for multimedia communications using our USRP devices. Then using this testbed, we then had to be able to transmit and receive raw data between two devices. And then the last thing was to expand this testbed to accommodate even more USRP devices, in addition to the original two. This would be done using a network switch to connect everything together. So now to break these requirements down into engineering requirements, we decided the common reliable frequency use would be the 2 to 2.4 gigahertz range. As this is a busy frequency range, we expect to encounter some interference, but that actually wasn't the case. To finish designing the testbed, we would then have to use GNU Radio, the software we decided to use for the project, to come up with a working transmitter and receiver. And then covering the second customer requirement was mainly testing out the first one. Utilizing the design testbed and making sure everything's working okay. We had to make sure the devices were communicating with one another and demonstrate a working file exchange between the devices. And then the last set of engineering requirements covers the implementing of additional USRP devices. And this entailed use of an Ethernet switch to which all the devices would be connected by Ethernet cables. And after configuring in these added devices, we would then have to again stress test the new system and ensure everything is sending and receiving okay. And so the only constraints we really had here were the specified frequency range of 2 to 2.69 gigahertz, and the USRP Ethernet drivers could only support speeds up to 1 gigabit per second. And then this is essentially our final setup of the project. You can see the Cisco Ethernet switch there in the middle that we connected all the USRP devices too by Ethernet cables, and also computers going into it. And then also out of each USRP device, we have antennas from which they'll be transmitting and receiving from. Each USRP device can be chosen to act as a transmitter or a receiver, depending on which GNU radio script we decide to enact on it. And then this is just a list of all the hardware and software we ended up using on this project. The 4 USRP devices, the VMware virtual machine we used, Ubuntu, and of course GNU radio was used for the software in addition to some Python scripting. And in designing our transmitters and receivers in GNU radio, we were considering multiple modulation schemes. There was the FSK method, where information is transmitted through discrete frequency shifts, and there was also the PSK method, where information is transmitted by changing the phase of the carrier signal. And in the end, we decided on phase shift keying, or more specifically, differential quad-district phase shift keying. It may be more difficult to implement because it requires a higher bandwidth, but it's more power efficient and it's widely used in today's data communication systems. Frequency shift keying may be easier, but it's also highly error prone and not optimal for what we needed. Now I'll pass this back to our team lead, Eric.
Yeah, so the image right here you're seeing is the new radio code for our transmitter. So I'll walk you through it real quick. So right here we have our file source where the data is being piped from, and it's being encoded in this packet encoder. That's setting the sample rate and the bits per symbol up to the modulator, the DPSK modulating scheme that Jeff was describing. And being amplified here and sent to our USRP device. In this case, the IP address can be changed with the script. It's a parameter that's passed to the script that can be changed, so it can interface one of the 4 devices in the network testbed. And the receiver end, it's basically the same thing, but in reverse. So you have, obviously, it's listening in on an IP address, a USRP device, and it's demodulating the signal, decoding it, and sending it to a file of your choosing. So we initially found issues with how this was designed, and specifically because the data that we were receiving was being transmitted over and over again. And if you look at the raw data, the packets that are coming in, a hex dump pretty much, this data just keeps repeating, and there's no distinguished start and end of the data. So when you're trying to open it on your operating system, it wouldn't show anything valuable. So what we did was we took a look at the hex dump right here. So for example, for a PNG image, something like this, which is essentially the PNG signature for all files with a PNG extension, that is something that the computer can recognize and interpret as a PNG image. But what we were actually getting was this right here, and this can't be identified as PNG, so the file we were receiving on the other end wasn't able to be opened and viewed for demonstration purposes. So you're asking, where did it end up? So obviously the transmission didn't start where we wanted, and it ended up being repeated at this point in memory right here. So you see right here, this is the packet start, PNG, and the I header. And I'll even show you basically how it is that we got to fix this issue. So right here, everyone's favorite plumber, Mario, is a test example. So on the top here, you see the header that I spoke to you about. And there's another piece of data, the IN chunk, that signifies the end of the data. So what our script was designed to do was to essentially find this signature and this chunk and take the data in between them and output it to view the actual image. Essentially what the script is doing is it's searching through the raw data and trying to find if there is a start and a finish, and take the payload in between and pipe that out to a new file for the user to actually view and have something significant to look at. And so like I said, we did the same thing, same process with text files, because again, text was being transmitted over and over again, and we just want to show a single message. So in our example, we have this symbol right here, the # signifies the head of the data, and that in reverse would signify the footer, or the chunk at the end of the data. And we're basically looking in our script for the payload in between those two. So whatever's in between these two signals, we know that's our data that we want to see, and we want to pipe that straight into the console to view when the user is receiving information on their USRP device. So I'll bring it over to Joey.
for our test plan, we essentially divided our system into two separate parts. One, the hardware, and two, the software. It's important that the hardware ends up working, or else you don't get a chance to test the software. This is just our basic tests for initializing the system. This checks for some of the most important features, like is it plugged in? We essentially just ran through it. We checked connections, made sure everything was connected properly, and once it was, we could use the UHD find devices command, and that command would output any USRP devices that were connected to the system. Following that, we started to work on software and file transfer. We ended up running through this several iterations of this. We ended up with a basic system that will successfully transfer files from one end of the system to the other. Unfortunately, our rate of success is less than ideal. There's currently only about a 70% success rate for 3 kilobytes, but that's likely due to the fact that we have no form of error correction in our code, and also that there is potential interference amongst the airwaves. We also believe that one of the major issues is packet loss, where larger files, when it's not sending the whole message or picture in one packet, it ends up losing most of the data. There's also the concern going forward of bandwidth allocation, because as you add more devices to the system, you're going to end up with more bandwidth needs from the switch and the network. Also, at the time being, the data rate that we get out of the system is only at about 11 kilobytes per second. Again, that's possibly due to interference or packet loss. We measured the data coming into the receiver and calculated how fast the data was coming in based on how much data we received in a set period of time. And I will pass to Kevin.
So this is our plan, how we planned and scheduled throughout last semester and this semester. Basically, each task were divided by us, and the green represents the task that we completed, and the red were the tasks that we kind of like delayed for later or something. So basically, our summary: the requirements were met on a small-scale environment. The project successfully accomplished, which means that we achieved the file transfer from one device to the other. The system is capable of taking in data packets in the form of modulated signals and interpreting that in an operating system as a valid data format. We of course had some issues. Larger files were unable to be transmitted efficiently, some because of data packetization. The data packets were constantly getting lost or scrambled, causing the data to appear either pixelated or incomplete. To fix that, we thought about using forward error correction, FEC. This method would basically help obtaining error control and data transmission, in which the source will send a redundant data and the destination. So also basically because the FEC does not require handshaking between the source and the destination, it could be used to broadcast the data to many destinations simultaneously from one single source. And with transmission errors, we viewed previous work done in the 600 level courses that corrected transmission errors and had more detailed encoding modules. So to make the project better and more efficient, we would have to better understand how networking and how radio engineering works.
So we have here a video demonstration of the application and run. First two will show transmitting and receiving a text value. So I will start playing the video right now. So right here, we are looking with the command to see which USRP device is active. So we will say to run the chat client for that IP address. And right here, we're telling it to type in hello world and send that to the receiver. So once we enter that information, we'll be prompted with the GUI right here that demonstrates the frequency spectrum, transmitting over 2.45 gigahertz. And go over to the receiving end. So on another computer, addressing a different USRP device, as you'll see here. So this IP address is a different USRP device in the network. Listening in for a chat, again, it'll prompt you, and it will end the application once it detects data, and it will output straight to the console the message that was received from the transmitter side. So now the next test is an image. So demonstrate here the image that I'm about to transmit. So picture of the Red Sox here. And what the script's going to show now is it's just changing directories to the source code, and it will again launch the application. This time, instead of saying chat, it will specify that it's transmitting an image, and it will be sent to the path that we identified here. And the IP address of the USRP device. So once again, when it's launched, it'll launch the GUI that demonstrates the frequency spectrum on the transmitter side. And on the receiving end, again, we're identifying that we're listening in for an image at that IP address. Take a little while for the data to come in, and now we're notified that the transmission has been received, so it's been saved into out.png, so we're running this command to go ahead and view the image, and here's the image that ended up on the receiving end. So that's the end of our demonstration. We can open forum now for any questions.